you have cases, what you do is you add up the number of ways to do those cases. So my final answer now, kind of messy. You don't need to simplify your answers, as you know. You take the 10, choose 6, you pull it out. That was from the very beginning. And you're just going to add up the two cases that we just talked about. So in the first case, we had 6 choices, then an 8, choose 3 came into it, and then a 5 factorial came into it. And in the second case, we had a 6, choose 2 came into it, followed by an 8, choose 2, followed by another 6, choose 2, followed by a 4 factorial. And we would just simply leave it like that. Does that make sense? So this is a great example. It's got the multiplication principle. It's got the addition principle. Cases are being used. Not a much simpler way to do it than that. If you guys are struggling with these, again, this is just, it might be that you need to go back and track. Remember the exam question, like the cats and dogs positioning for photograph? This is like that kind of problem. Or there's the ones with the flag. I think they gave you examples with flags, with colors and stuff. This is like that kind of problem. So you'll see a lot of examples that are like this if you just look. So I just wanted to do another one to kind of remind you about that. Okay. Let me see. About 30 minutes. I won't get through everything, but I'm doing quite a bit here. Skip that one for now. Okay, let's do number 16. Okay, 16 is this one. This says, I'm going to abbreviate the question here. Let a sub n equal the number of ways to tile n walkway squares if the tiles are either red, green, or yellow, so that no 3 red tiles are consecutive. And the question then is going to be, find a sub 7. Okay, does anybody recognize this kind of problem? If so, what does it have to do with? Yeah, this is a recurrence relation, right? Basically, you have a walkway of length n, and you need to figure out a formula for it. Okay? So, what would you do to start analyzing it? Okay, yeah, we have cases. So for solution, we use cases. How do you want to break down your cases? Okay. So there's three cases. There's red, there's green, and there's yellow. So I'm just going to abbreviate like that. Now, are these all going to be the same? Treated kind of in the same way? You see, if your walkway starts with a green tile or a yellow tile, then if you look at the remaining squares, right, if they're going to be, essentially what you can do is you can tile the n-1 squares that are left subject to the same rules. So they're going to be, a sub n-1 walkways of length n in that case, right? Because you're not going to have 3 consecutive reds there. So basically you're taking legal walkways of length n minus 1 and tacking a green tile onto the beginning of it. And then you can do the same thing with the yellow one, right? Same thing with the yellow one. So this is going to be the same down here. But then, can I just leave this like this? You see, the problem with this is that there are legal walkways of length n minus 1 that don't have 3 consecutive reds, but when you tack a red onto the beginning of it, now it does have 3 consecutive reds, which means you didn't want to count it. So the problem here is you don't want to leave that alone. So what do I need to do here? Split this up into other cases. If I have a red here, then, for example, if it's followed by a green, then I'm fine. And at that point, any legal walkways of length n minus 2 can be considered, and I just add a red and a green in the beginning. So a sub n minus 2 walkways here of that type. I need more. Sorry, my writing is in the wrong order here. I also have a red-yellow pattern, which is going to be the same. Okay? And I can have red-red, right? I can have red-red, but then I have to follow it, right, with either a green or a yellow. So red-red-green, red-red, yellow. Right, there'll be a sub n minus 3 here, a sub n minus 3 here. Is everybody okay with this? So your formula for a sub n is just the sum of those. The only pattern that isn't here is red, 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 which is not legal anyway. We don't want it to be there. But everything else is listed there. So it's just going to be 2 factors of a sub n minus 1 plus 2 factors of a sub n minus 2 plus 2 factors of a sub n minus 3. Right? That's an order 3 recurrence relation. And that is, I mean, I could ask you to solve this, but you have to be able to find the roots of the characteristic equation. And that may not be so easy. What else am I going to need here for this problem, by the way? Initial conditions. And what values would you suggest I use for initial conditions? What values of n should I use for initial conditions? You need 3 of them, right? You have to have 3 of them because the recurrence relation has order 3. So if it's an order 3 recurrence relation, you got to have 3 initial conditions. So which 3 do you want me to use? A sub what, and what? 1, 2, 3. Don't use 0, guys. Don't use 0. Walkway of length 0 doesn't make sense. And it can be confusing to do that. So how many walkways of length 1 don't have 3 consecutive red tiles? There's only 3 colors, and any of them will work, right? How many walkways of length 2 don't have 3 consecutive reds? 3 choices for the first tile, 3 choices for the second tile, and I don't have anything to subtract because they're all good. Right? And how about for A3? Yeah, see, there's 3 choices, 3 choices, and 3 choices, but the red, red, red one has to be subtracted, so it's only 26. And now from here, to find A7, I'm not going to go through it because I want to move on, but basically you just plug into this formula. By the way, I don't like, okay, it's not wrong to do this, but let me tell you something I don't recommend that you do. Some people I saw on the second test, they did something like this. They said, oh, A7 is 2 times A6 plus 2 times A5 plus 2 times A4, and then they start plugging in back substitute. So A6 is then, 2 times A5 plus 2 times A4 plus 2 times A3, right? And then they plug in this one into 3 terms. And, right? This is not wrong, right? But what we're going to end up with is a mess, right? Don't do that. Just build up from A1, A2, A3 to what is A4, what is A5, what is A6, and what is A7. You don't need to be breaking it down. This will work, but it's going to be a lot more writing and a lot more time. So I don't like this way here. Okay, does that make sense? All right. Do you guys need practice on solving recurrence relations, or do you know that for the process? You're good with that? Remember that we have homogeneous and we have non-homogeneous recurrence relations. The non-homogeneous term is usually either polynomial or exponential. And you have to use the initial conditions to find the constants. I'll skip that. I'll let you guys do that one. Let me just think which ones would be. Let me give you this one. I want to do the hardest ones. So I think the easier ones you guys can try on your own. Let me give you another one that I think is a little tricky. If you have the handout, it'll help, but I'm going to draw a fairly complicated graph. If you don't have the handout, it's all right. You can always just look at what I'm drawing and not try and draw the whole graph. So this is number 19. Is G planar? Is going to be the question. So here comes my graph. So we have A to B, C and D are here and here, over to E, and here's F to G, which have a bunch of points around the circle, H to I, and then I goes back to A again. So that's kind of the outside structure of it. There's no edge from B to C, and there's no edge from B to F. And then A is also connected to D and E and G. No, I'm really strong. A goes to G, like that. And B is connected to E and F. And C is connected to F. And I've already got E, or B. E goes to H as well. And then F also needs to go to I. I believe that's everything. So let me make sure everybody gets that graph. The question is this graph planar or not? When you hear a question like that, what sort of things do you think about? Crossing number, yeah, crossing number 0. That's really what planar means. What would you say? Okay, the Euler formula is involved. That's the one that says, oh, that might be another nice one to ask. That's the one that says that the R minus E plus N is equal to 2. Remember, you first prove it for a tree, and then you just start adding edges, which increases both E and R by 1 each time. Preserves that inequality. So this is the Euler formula. And what else do you, let's just get a list. What are some other things that come to mind here? Stephen?
Circles and squares. Like you said, vertices are connected.
So when we put circles and squares around the vertices, we usually do that to decide if something's bipartite. It's a slightly different concept. Davey?
I think K5.
Okay, K5. Why do you think of K5?
Because K5 is not planar.
Okay, is not planar. So if there was a K5 inside of this graph, then the answer would be no. Okay, there's various inequalities, right? So if G is planar, then which inequality can we always use? Right, it's E is less than or equal to 3n minus 6. So if this weren't true, if this were not true, then your graph would be not planar. Now, if G is planar, and there are no 3 cycles, then there's a better inequality, a sharper one. Does anybody remember what that is? Okay, you guys all need to know these. E would be less than or equal to 2n minus 4. And then we even did one more in the group work. If G is planar and there's no 3 or 4 cycles, does anybody remember this one? Exactly, 5/3 n minus 10/3. So that was actually in the group work. And then I think on the exam, I asked someone, I said, what if there's no 3 cycles, 4 cycles, 5 cycles, or 5 cycles? So you have none of those, then there's even another one you can write down. Okay. Don't worry about memorizing infinitely many of these. Okay, but the first couple of these you should know. Now, if there are 3 cycles, but there are no 4 cycles, am I allowed to use this one? Okay, if there are any 3 cycles at all, then we can't start using any of the inequalities beyond the first one. Okay, has anybody, while I've been blabbering up here, figured out what N and E are? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. I think N is 9. And to figure out the number of edges, we add up the degrees and divide by 2. So let's see. 5 plus 3, that's 8, plus 2 is 10, plus 3 is 13, plus 4 is 17, plus 4 is 21, plus 3 is 24, plus 3 is 27, plus 3 is 30, divided by 2 is 15. Okay, 15 less than or equal to, so 3 times n minus 6. The 3n minus 6 one doesn't work, because it just gives me 15 less than or equal to 21. Okay? Can I use the better inequality? Are there 3 cycles in that graph?
Yeah.
There's not very many, but there is, yeah, A, D, E, there's a triangle right here. Okay? So I can't use that, so this whole game plan right here, although I was very happy to review it, doesn't work. Okay, it's still good. We gotta review this stuff. Okay. All right, so that doesn't work. Anything else that we haven't? Oh, K33, exactly. So K33 is another one. So K33 and K5 are both not planar. Right. So if I happen to have a subgraph that is isomorphic to either of those two. And does everybody remember what K33 is? This is the complete bipartite graph. So that's the one where you have 3 vertices in one camp, 3 vertices in another camp, and you have no edges between the vertices from the same camp. They only go across camps. And you have all of those edges in the case of the complete bipartite graph. So I guess the question is, does anybody see anything? Is there going to be a K5 in here? Let's see, K5 is this one. Right? There's a whole lot of vertices at degree 4 there. Right? If you look over here, gosh, we've got one vertex at degree 5, but we've got 2 vertices at degree 4, but everything else is less. It's not very promising. Does anybody see a K33 in this graph? Unfortunately, there's no magic theorem for this. You'd have to look at the picture and see if you can come up with 2 camps. If you're struggling to come up with something, by the way, this is a place where, like it's on a test, if you tell me these facts, you say, well, I believe there's probably a K33 in there, and I know of this fact that if there's a K33 subgraph, it's not planar. I just can't find it. That would be good to write down, because then I can give you credit for knowing the fact. I can't give you full credit for the problem, but I can give you partial credit for knowing the right tool to use. What is it? Yeah.
Is it safe to get rid of the edges coming from C, since there's only 2 edges coming out of C, when you try and find the K33?
I wouldn't get rid of it. You'll see why in a second. I wouldn't get rid of vertex C.
No? Oh.
I wouldn't remove anything off of this graph. Okay guys, I'm going to help you with this. I know we've been at this a while, we're getting a little tired, and that's fine. Look at vertex A, H, and F, I believe. and F, right? Now, that's going to be one of my camps. Okay. Now, my other camp is going to be I. So I put a square here. Notice that that one is adjacent to all three of the circle ones. And G, which is also adjacent to all of the three that are circled, but not to the other one that's in the same camp. And now here's the trick. You're going to not like me for this, but vertex E. I'm going to put this here, and I know what you're thinking. Okay, so let me first explain. So vertex E, everybody hopefully agrees that it is not adjacent to either of the other two vertices from the same camp. So is it connected, because it's supposed to be complete bipartite graph, so it should be connected to all of the circles. Well, it's connected to A, and it's connected to H, but it's actually not connected to F. So it doesn't look quite right, does it? But here's the point. So if I want to draw, let me just kind of draw how this would look. So here's A, H, F, and I, G, E. And I'm just going to draw the subgraph that we have. We do have A connected to, I, G, and E. And we do have H connected to I, G, and E. And we have F connected to I, G, but not E. So it's not quite K33. Right? But bear with me for a minute. Imagine I put that edge there, and I'm going to imagine that there were a couple of other vertices along that edge. Now by putting those vertices along that edge, of course, now F and E are no longer adjacent, because I have made new vertices to put there. I think, you guys remember when I showed you, like, you have like a K5 or a K33, you start putting dots on the edges, right? You're not changing the crossing number by doing that. You're not taking, if by putting these two dots here, you're not taking something that was planar and making it not planar, or taking something that was not planar and making it planar. You're just adding a couple of dots, but these segments are still there. The fundamental property that this graph is not possible to be redrawn without any crosses is still true. You can't do it. So this is still not planar. This is really just a modification of K33. And what I want you to notice, and this is why I didn't want you to erase vertex C, is that E and F, although they're not adjacent to each other, if I add a couple of other vertices, so if I put a D and a C here, right? Essentially, that's creating this basically, this edge from E to F is just being twisted the long way around. So I would not say that this graph has K33 as a subgraph. It's not quite K33, but it is what we call homeomorphic to, or basically you can just simply add these two vertices along that edge, and then it's the graph that you see as a subgraph of this graph. Okay? So therefore, since the graph has a subgraph that is kind of, I'll put this in quotes, homeomorphic to